What's up to anyone who's just signing in? So I will wait for the chat to get going here and we will start answering some questions. So let me just log into my Vinteachers Math email so that when people have custom questions here that they just want to copy and paste, we'll be ready to go. Yeah, so we're on a little bit early today, but I'm going to probably go till about 9:30, maybe a little bit later, and then we will have to call it a day. But welcome to week 9. Very excited to get this stream going here. Question 34 from the packet of fun. All right, so thank you, Max. We'll get this going right away. So let me just display source. I'm going to I just have to go browsing here and find the packets of fun. So let's see. I should just have those on standby, but I don't. All right. Packets of fun. Let's see. 20. Why is that not the first thing? All right. You know what? I'm just going to type it in. Packets of fun. Here they are. All right, we are on. So let's see, packet of fun 34 optimization. Okay, so this question, I'm just gonna jot it down here. So this is the area of the largest rectangle. So what we want is we want the largest rectangle. So the largest rectangle that can be drawn. So let's go ahead and get a visual of this. So the largest rectangle that could be drawn with one side along the x-axis and two vertices on the curve y equals e to the negative x squared. So when I'm thinking of y equals e to the negative x squared, I'm thinking of something that looks kind of like this. So then let's just see the area of the largest rectangle that could be drawn. One side is on the x-axis and two vertices are on this curve. Okay. So let's think about this. The area of the largest rectangle. Oh, wait a minute. E to the minus x squared. Wait. This does not look like this. All right. So what I'm getting from this. So let's erase that. So e to the minus x squared. I don't know if this is necessarily in the. We're not necessarily in the calculator part. But e to the minus x squared. So one thing that just jumped out at me. So I hit a roadblock because I was like, wait, you can't get two vertices here. But one thing I'm just imagining here, if I don't have a calculator, is like x and y. At 0, you have e to the 0, which is 1. However, no matter what values of x you plug in, if you plug in x equals 1, you're going to have e to the minus, and then 1 squared is 1. But if you plug in negative 1, you're also going to have e to the minus 1. So this thing looks something like this. Let me make that a little nicer. It's going to be. So this is an even function. Has symmetry over the y-axis. Oh, my screen. That really does help if you turn the screen on. Okay, so the largest rectangle and y equals e to the minus x squared. So it's going to look something like this. I initially went to just draw something that was like just kind of like a exponential but flipped over the y-axis, but the minus x squared is what's going to happen. Yeah. All right, so let's take a look here. So the idea is that you're going to put two vertices on the curve like this. So here's our rectangle. And this rectangle, the dimensions are kind of like the one we did in class today. So x comma y, so this distance is x from the origin over, and then this is x, and this is y. So this is another one of those, the area is 2xy. But what you would do here is you would say the area as a function of x is equal to 2x e to the negative x squared. See, we're just replacing the y. So now from here, if you want to find the maximum, you're going to do a prime of x equals, and you'll have product rule, 2e to the negative x squared plus 2x e to the minus x squared, and then times minus 2x. So this one is looking like 2e to the minus x squared minus 4x squared e to the minus x squared, which would be e to the minus x squared times 2 minus 4x squared. Now, one thing to be mindful of here with this question is the area of the largest rectangle. So this is a concept here that let's just set the domain to be x is greater than 0. You know, we could say x less than 0, but let's say the x we're looking for is in quadrant 1. That'll make things, you know, a little bit easier to deal with numbers like this. So now this is always positive. So we're not going to get a 0 out of this. So a prime equals 0. That's only going to be true when 2 minus 4x squared equals 0, which is going to be true when, let's just see, if we have 2 equals 4x squared, so x squared is equal to a half. See, like, I mean, I'm kind of skipping steps here, but, you know, we could just add the 4x squared divided by 4, and that tells us x equals square root of 1 over 2. I could say plus or minus, but we're just going to look at domain x greater than 0. So now, what we want to find here is the actual area, and our area function is this. Now, one thing here, because none of these is not an answer, that means we're just going to plug in x equals positive root 1 over 2. But if I had to go the extra step, like let's say this was kind of like a free response situation and I want to explain, then I have a prime and I have radical, you know, 1/2. And if we plug in something like, I don't know, let's say radical 1/4 here, then what we'd get out of this is if we plugged in, you know, square root of 1/4, which is equal to a half, and you work this out, you're going to get a sign change here from positive to negative. So that's just how we know it's an absolute maximum. But now I just have to plug that into the a of x function. So I have a of radical 1/2 is equal to 2 times, and what we have is we've got radical 1/2, and radical 1/2, that's the same thing as 1 over radical 2. So I could do this times e to the negative, and then x squared is equal to a half. See here, so x squared, this part, is equal to a half, so e to the minus x squared would be e to the minus half. Now we look at the answer choices, and are we seeing that one? There's a radical e on bottom. Let's just see. I'll clean this up a little bit. It's probably going to pop up as something else. So this is 2 over square root of 2 square root of e. And this one I could say is radical 2 like this. I could just rewrite 2 on top, and then those will cancel. So this is radical 2 over e. I'm hoping that's the right one. You could double check me on that. I hope it's that. Let me know if it's not, Max, if I messed up somewhere. But that's the idea. Okay. So yeah. Justin W. So let's hear. So kind of like a Q&A situation. In college and struggled a lot with class of late. What's your advice on not losing faith in math? Oh yeah, it worked. Okay, I'm glad, Max. All right, so this is at Justin W. Now, it's hard when you're in it, you know, like when you're in the process of like you're not doing amazing in a class. Like I remember, it's, you know, it kind of sucks. And the key is though that each day you got to do what you can, and you got to give yourself time to grow. You know, the example we learned, I just read this like good book. I read this book last week, and I've been reading more. I'm trying to, like, instead of watch TV as much at the end of the day. I mean, I still watch TV, don't get me wrong, but I read this book. So, Atomic Habits. It's a pretty good book, but it's all about, like, you make minor changes each day. Oh, you did the product rule wrong. That's all. All right, no problem. I'm glad it makes sense now. But if you're struggling, all you could do is, like, it's hard to make a drastic change and really stick to it. But the idea is that, you know, if you want to see changes, I'll use the example of an exponential function. Is that this is like the point where, and I'll make it even less steep because that's like a pretty steep one. So let's say it takes a pretty, like, long time to launch, something like this. Okay, so this is like your success versus your effort. All right, I hope I'm spelling things correctly here. Sorry, it's been a long, that doesn't seem right. Let me just see. That is correct. Okay, sorry. Yeah, just at the end of the day, when my brain is fried, sometimes I'm like doubting my spelling, but it's correct. Good, I could still spell. All right. You ever have that? Like you look at a word and you're like, is that really a word? And it's like something simple. It could be like the word let. And like, it's like, wow, let. Like, what is let? Like, you have like an existential crisis. I think I just had one on success. Like, is that really how you spell it? Like, what? But all right, that is how you spell it. But what's the point of this? So this is still at Justin. So what happens is, like, what people wind up thinking is they start, like, this is where, like, they maybe like around here. It's like, all right, start trying. You know, like I want to be successful. I want to be motivated. I don't know how to get motivated. But the key is you got to do a little bit each day. And you make little changes for the better. You know, something as simple as, like, you take your cell phone and you put it 20 feet away from you when you study, you know. And then maybe every half hour you reward yourself and you look at a text message or something. So little things like that, but you put in a little effort each day, the little changes for the better. And most people, like, they get here and they're like, oh no, it's not working. You know, like I don't see results. But what happens is, if you do these, like, little things each day and you don't take days off, and if you take a day off, like, you don't fall into this bad spiral where you just keep messing up. But little changes each day, it's like you have to give it time for you to enter the exponential slide. Because I've seen it happen with students, like the kids who, like, they're committed, and they stick with it for more than a day. It's like whoosh, like you just go. So yeah, at Justin, that's the idea. Like I said, it sucks when you get bad grades. I've been there before, but you got to keep moving, keep going, go past this point. Okay, just try to enter the slide, and then when you enter the slide, it's like awesome. Very slowly. The thing is, people don't realize how long it takes to, like, hit that next level. But when you enter the next level, it's going to be, like, dramatic all at once. You know, it's like a slow grind, and then just, like, whoosh, like you just go. So just hang in there. You know, you will get there. All right, let's see. So next question, Jada 738 in the AP Calc problem book, page 76. So let's see, 738. No problem. Any way I could help. Like, it's frustrating if you're not doing well. Like, but it's like a part of things, you know. That's just how. Oh wow! So we want to. So at Jada, I'm impressed. 738. You want to learn particle motion? I could show that. I mean, even though it's like a little bit out of, you know, the range of what we've been doing. So let's see, x of t equals 3 pi over 2 t squared minus sine of 3 pi over 2 times t squared. Okay. And for part A, let's say you want to find an expression for velocity. Well, velocity, if x of t represents the position. Oh, that's good. I'm glad. Hey, don't ever lose that curiosity. All right? Don't ever lose it. So what we have here is a particle is moving along the x-axis. All right. So this is like kind of like a calc AB style one. So unit 9, I would like kind of hang tight because there's a lot we have to learn with parametric equations. But a particle moving along the x-axis, it's like this thing could just go like to the right and to the left. You know, it may go to the right for a long time, for like 20 seconds, and then it might go backwards for 3 seconds, go forward for another 1,000 seconds, go back for 10,000 seconds. So this thing is just moving left and right. And x of t, this tells you like position, like tells us where the particle is. All right, so that's like really what it's telling us. Like, let's say, you know, if I were to plug in something like x of 0, that's the easy one to plug in. I would get 0 minus sine of 0, which is 0, which means at time t equals 0, like if you consider this the number line, like 0, 1, 2, 3, and I will erase this part, that the particle is like at 0. So at t equals 0, this is the position of the particle. It's like right here. All right, and if you were to plug in, let's say like x of 1, that would give you 3 pi over 2 minus sine of 3 pi over 2, which is going to be equal to 3 pi over 2. And this is equals -1, so minus 1 is this. So that's not a polite number. So like wherever that is, that's where we would be 1 second later. Okay, so that's just giving you like some kind of like intuition on like what's actually happening, because it's really good to be able to imagine what's actually happening when you're doing these questions. So part A, they ask you to find the velocity, and like that's just technique. So you say, all right, velocity is the derivative of position. It's the rate of change of position. So velocity would just be equal to, we'd have the constant 3 pi over 2 times the derivative of t squared is 2t. And then minus chain rule, we do the derivative of the outside as cosine, keep the inside as 3 pi over 2 t squared, and then multiply by the derivative of the inside, which is 3 pi over 2 times 2t. Now if we simplify things a bit, this tells us our velocity function is equal to 3 pi times t minus, and then 2 over 2 cancels, and we have 3 pi times t times cosine of 3 pi over 2 t squared. All right, so that's velocity. Acceleration, so this is part A. Acceleration is the derivative of velocity, which this is going to get, you know, a little bit annoying because, how we say it best? It's going to get a little annoying because now we have to do the product rule. So for acceleration, I would just be a little bit careful. I would take my time. So acceleration is equal to the derivative of 3 pi t with respect to time is 3 pi. And now we have to do the product rule. If you need to, you could say like, you know, u equals minus 3 pi t and v equals cosine blah blah blah, but I'm just going to go ahead and do this like the faster way. So we have minus, we have the derivative of 3 pi t is 3 pi times cosine of 3 pi over 2 t squared, but now we have another minus 3 pi t times the derivative of cosine is negative sine. We keep the inside as 3 pi over 2 t squared, but now the derivative of the inside, as we saw before, was just going to give us 3 pi over 2 times 2t, which is 3 pi t. So I'm just going to tack on 3 pi t like this. Okay, I will move all of this stuff over. So this whole mess we will move over. Okay, so now just clean that up a little bit, and let's see, acceleration as a function of time is 3 pi minus 3 pi cosine 3 pi over 2t squared. And now this one's going to change to plus, and we have 3 times 3 is 9. Pi times pi is pi squared. Yikes, this one's a mess. T times t is t squared. And then we've got sine of 3 pi over 2 t squared. Let me just make sure I'm not messing that up. Plus 9 pi squared t squared. All right, that seems good. Yeah, these are like kind of just, that one was like just a little bit tedious. Now part C, we want to know when is the particle at rest. Like blah, 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 particle at rest. So the concept for this, what I think of, when something is not moving, it's just still. So yeah, this is like not moving. It doesn't matter where it is, but what does matter is that anytime something is not moving, the velocity is equal to 0. All right, so that's the idea you want to use for this. So then what we do is we take the velocity function and we set it equal to 0. Find the values of t. So v of t is equal to 0 when, and we take this. And what I would do, like kind of preemptively here, is just factor out a 3 pi t. And you're left with 1 minus cosine of 3 pi over 2 t squared. Now, this one is just obvious. It's like t equals 0. So yeah, if we plug in t equals 0, the particle is at rest. Now, they didn't specify, oh, between 0 and 2. So the original question we should mention is between 0 and 2. So in a moment when we start looking for answers, we're not going past 2. All right, that restriction on the domain is not going anywhere. That makes life a little bit easier because then we don't have to like make an index. So 0 to 2. And now we have t equals 0, but now this one. When is 1 minus cosine of 3 pi over 2 t squared equal to 0? This is true when 1 equals cosine of 3 pi over 2 t squared. And now what I think of at this step is I think of all the times cosine is equal to 1. I know cosine of 0 equals 1 because of the unit circle. Remember, the unit circle is life. Okay, cosine is equal to 0 at the point 1, 0. So that's 0 radians at 2 pi radians, at 4 pi radians. So every time I spin 2 pi, this is what we get. Because we're between 0 and 2. We're not going backwards or anything. So then what that tells us, well, we already took care of t equals 0. But what about when the inside, this piece, when 3 pi over 2 t squared, what about when this is equal to 2 pi? Well, now this is just algebra. So now we multiply by 2 over 3 pi. And now see you later to this. And that gives you t squared equals. And you're going to have the pi's cancel, and you're going to have 4/3. Take the square root. Remember, t is between 0 and 2. So this tells us t equals 2 over radical 3. All right, let's just make that a little bit neater. So t equals 2 over radical 3. The next thing I would try is what about 4 pi? Because 2 divided by this is, like you see here, like we can't go past 2. And something's telling me when we go to the next one, that's going to be a problem. So this is like one answer. But if we do the inside, 3 pi over 2 t squared, we set that equal to the next one, 4 pi. I bet this one might be a problem. So the pi's cancel, and this is going to give us t squared equals, multiply by 2/3 on each side, you'll get 8/3. Okay, and here's the problem, that t equals the square root of 8 over the square root of 3. Now, what's wrong with this right away, let's just see how this is going to work out. So 2 and change over 1. Or actually, is this one going to be okay? Yeah, this is where like these get a little annoying because let me just see, radical. Well, this one maybe I'll just write like this. This is like the square root of like 2.666 like repeating. So I guess once this goes past 4 is when it's a problem. Like you see out here, it's like 1.3 repeating. So like this one looks good, but then I would do 6 pi next and see when it runs out. So like I'm not gonna like I won't keep going through all of them. Like honestly, I would use a like this would be a calculator situation. I feel like they wouldn't make you do this much work in the free response. Like that's just like kind of tedious after a point. And find the position of the particle at the times found in part C. Like you would just then like for part D, you just plug this in to x of t, and that'll tell you the position. But calculator all the way for sure. But good question. That's an intro to position, velocity, acceleration. I really love these questions because like it's fun for me to like try to stay fresh on the stuff we haven't covered yet in class. So I like, having to remember it like, without preparing. It's fun to think out loud because like I'm showing you all like how I go back and relearn stuff. Alrighty, so 554 or 550. Yeah, technique is definitely not bad. But that's the thing, Jada. They would not make it so the algebra is like just insanely tedious. Like they do have a line with AP College Board. And same thing with colleges. Like they're not going to give you a question that takes like 3 pages of algebra. But like I'm just showing you like the thought process of like how the algebra is totally doable. For sure. So we have 554 or 550, somewhere in that range. All right. So let me scroll back. Yeah, this problems book I love. It's a great book. Ooh, all right. This is a good question. So 554 or 550. So let's see. 554 is a right circular cone and a hemisphere have the same base. The cone is inscribed in the hemisphere and its base. Oh, that's a fun one. All right. I'll look at 550 first because 550 is like definitely easier. I mean, who knows? Maybe it's not easier, but I'm just assuming because it's like less words. Like that means there's less to keep track of. So we have a particle moving along y equals radical x. And so this is like, 550 in the problems book. And at what point on the curve are the x and y coordinate of the particle changing at the same rate? So here, what I do to bring these questions to life is I draw it out. So here's square root x, make it a little neater. So we want to know just at what point on the curve are the x and y coordinate of the particle changing at the same rate. So my first instinct here is to call it this and then take the derivative with respect to time. All right, it's totally going to happen where like someone's going to throw me a question and it's going to take me like really long to figure it out. And I'll say like, all right, I'm going to put this on the back burner. So yeah, there are some related rate questions that like I would really need to like sit with them for a long time to be able to get. Like it's not like every one of them I'm just like, oh yeah, 5 plus 5 is 10, duh. But I'll do my best to always get through the questions that are thrown at me. So this is, so let's see, a particle is moving along the graph y equals radical x, and at what point on the curve are the x and y coordinate of the particle changing at the same rate? Okay, well, when they are changing at the same rate, x and y, so that phrase right there, at what point is the x coordinate and y coordinate like changing at the same rate? Like just that phrase alone in math language is saying like dx dt is equal to dy dt. Like that's what it means when they're saying that the x and y coordinate are changing at the same rate. So if they are changing at the same rate and they're equal, that means that these things like essentially cancel each other out. So like you could divide this side by dx dt and this side, And these just cancel, but because dx dt and dy dt are equal, if they're equal, that means this is going to cancel out, and we're going to have 1 equals 1/2 x to the negative half, and then the rest is algebra. Let's do times 2. So you have 2 equals x to the negative half, and then to solve for x, just raise both sides to that reciprocal power. So to the 2, negative 2 over 1 power, or just to the negative 2. Because when you multiply this times this, you're going to get x to the first. And then that's going to be 1/4. So it looks like here x equals 1/4. And since y equals square root x, then y would equal square root of 1/4, which would be 1/2. So that would be at the point 1/4, comma 1/2. That's my bet. I will look up the answer though, if they have it in the back. Oh, found in 5 sections. Yes, it's correct. Yay. Cool. That was a good one. That was a fun one. All right, and then, yikes, the next one looks, oh wow, 1970, Calc AB. All right, let's see. So that one, I'll give it a shot. Why not? If I get stuck, like whatever. The thing is, like, you know, as a teacher, I feel like, not that I've ever seen teachers like necessarily do this, but sometimes, like, you know, teachers, they don't want to like students to ever see like if they're stuck or confused. But like, I don't know, I'm the type, like, I don't want you all to think like I'm some, like, I don't know, like mythological creature or something that never gets anything wrong. Like, I totally get stuff wrong. So like, I'll give it a go. We'll see how this question goes. So what we have is, we have a cone, right circular cone. So we have a right circular cone, and we have a hemisphere. All right, blah, blah, blah. And they have the same base. Okay, so what I'm imagining here is, like, you know, we have some hemisphere like this. And what they're telling us, the cone is inscribed in the hemisphere. So that means, like, the cone itself is like going in like this. That was not my best artwork. All right, a little bit better. So hopefully you can imagine that. Now the figure is expanding in such a way, so the figure is like going out. It's expanding in such a way that the combined surface area of the hemisphere. All right, so a hemisphere, just know the area, volume of a sphere is 4/3 pi r cubed. The surface area of a sphere, it's actually like the derivative. You just do 3r squared times this, you'll get 4 pi r squared. So the surface area of a hemisphere, so now we have like the surface area of a hemisphere is 2 parts. It's half of the full, like if we had a full sphere like this, like all the way around, the volume is this, the surface area is this, but that's just like the outside. So this would be 2 pi r squared plus the area of this piece here with like radius r, like the part that's like kind of chopped in half, that's just a circle. So that would be plus another pi r squared. So the surface area, like, combined in this question. Okay, so this one they're saying here is the combined surface area of the hemisphere and its base. So this is surface area of the hemisphere and its base. That's going to be equal to 3 pi r squared. Okay, so that's just getting the question started. All right, so now the figure is expanding, blah, 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 that the combined surface area of the hemisphere and its base is increasing at a constant rate. All right, so this, like ds blah, 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 dt is equal to 18 square inches per second. All right. So at what rate is the volume of the cone changing? So what we're looking for is dv over dt. and this is for the cone. At what rate is the volume changing at the instant when the radius of the common base is 4 inches? So specifically when r is equal to 4 inches. All right, so this is just like kind of extracting stuff and trying to understand like what on earth is even happening here. So like just making sense of the question is like a big part of it. So now here, what we would do is we would take this equation and take the derivative. So ds of the combined hemisphere and its base, dt, is equal to, we would have 6 pi r dr over dt. And then from here, oh, one thing we should point out is that this cone, notice that this is also equal to r. Because it's a hemisphere, the distance from the center to any point on the sphere is r in any direction. Okay, if I were to go like from here to here, like that would also be r. So that's a big detail that we're going to need in a moment. So that's this. And now ds dt is 18. So I'm just going to write it without this. So at r equals 4, we're going to have ds dt is 18 equals, and we've got 6 times pi times 4 dr dt. And now we just divide both sides by 24 pi, which would cancel this out completely. And this tells us that dr dt equals, and this if we divide by 6 top and bottom is going to give us 3 over 4 pi. Okay, and the units is inches per second. All right, so that's our units. All right, so this is like one of those two-step equations. All right, I'm really hoping this works out nice. Okay, so now the volume of the cone is 1/3 pi r squared times h, but notice h is equal to r because it's inscribed in a sphere. So like just know like the height is equal to r, which gives us, I'll just say it like this, that volume equals 1/3 pi r cubed. So now we solve this. Oh, hello to everyone just joining. And Matt Lahita, help me. I will get to you soon. So let's see, pi r squared when we multiply. So we have 3 times a third canceling, pi r squared dr dt. So then at what rate is the volume changing? We have dv over dt at r equals 4 equals pi times, this is going to make 16 when we do 4 squared, and then we have times 3 over 4 pi. The pi's cancel, and 16 over 4 is 4. 4 times 3 is 12. I'm really hoping this is 12 cubic inches per second. So at Dory, I don't know if you have the answer key, but I hope it's that. That was a fun question. I like that one. I really like that question. That was a tricky one. But yeah, I believe that's it. If I messed up somewhere, I'm sorry. But let me know. If I messed up, just let me know in the chat. Oh, wait, I could just look it up. What am I saying? I'll just do a quick. Calculus. This is calculus. If you have a different question, so at Only for Nerds and Matt Lahita, you can let me know. Oh, it's right. Yay. It worked. Okay. So let's see. Next up, what other questions do people have? So yeah, thanks to anyone who has stopped by. Thank you. I'm glad we have people here. Wow, we're already 40 minutes in. This time really does fly. Yeah, my hat's off to the people who have me in person for a double period math class, and you're choosing to stick around for yet another period, maybe 3 or 4. So don't ever lose that motivation. How long does the live last? I usually stay on for an hour, so 8:30 to 9:30. So I got another 30 minutes. Sometimes I go a little over, but I don't know. I think I have to kind of start capping it at 9:30. Like the thing is, like what happens at Only for Nerds is my old students come by, kids who graduated like 4 years ago, and if they stop by in like the last minute, it's kind of hard for me just to be like, oh hey, haven't seen you in 6 years, like see you later. So I like sometimes go over like for special occasions. Like if it's within reason, I'll stay like a little extra. I'm not gonna do like an hour extra, like oh, just teach me all of like algebra 1, I'll say like come by each week and ask questions. So only for nerds, if you have a high school level question or a question that goes up to calculus 2, I'm happy to help. Now, the only topic I don't know from high school, I'll just be brutally honest, is AP statistics. I've never taught that class. And the last time I taught stats was in 2008, or took stats was 2008. So I would have to relearn it. So I wouldn't really be as much help on that front. But if you have any specific questions, sometimes like people put like study questions or math advice questions, just general ones. So either one I'm just happy to help with. Oh, also we got 13 people on. Very nice. 13 is a nice number. This is like one of my smallest class has like 25 people. So this is like a big chunk of my smallest class. So it's nice to see this live stream grow. I know second half in the spring, once we get closer to the AP Calc test and the Regents exams, like the end of year exams, it'll be really interesting to see how many people we get on here at once. So I have to spread the word for AP Calculus and the other subjects as well. I was thinking of like advertising on Reddit, but I know sometimes people get like funny about you advertising on a subreddit. Like, they say like, oh, don't self-promote. But I got to do more homework on that end. 37 of the fun packet. Absolutely. I would be happy to do one of those questions. All right. So 37. I just hope I know it. There's some packet questions that are just obnoxious. So let's see. Oh, okay. Advice for multivariable calculus. So if I had to relearn multivariable calculus, which I'm going to over the summer, my style of learning any math is like I learn it in like stages, almost like a pyramid kind of. I don't know why I said I'm drawing a pyramid. I promise this is not a pyramid scheme. And I guess if I have to start this with this is not a pyramid scheme, you're going to feel like it is. But here I just like I just kind of copy like examples, like this is like level 1 of understanding. Like I just copy examples and I like try to like, sort of like approach a level where I'm like fluent in the technique. Okay. So like this, you could do pretty well in a class. Like you could get probably like getting just fluent in technique. Like you could get like a B+, A-, like maybe pull off the A. But I would say like as you move up, you understand why it works. Okay. Now you're heading into like the A- A range. If you could understand like why it works, and then like here, like you could prove. So I don't know why I wrote a letter B. You could make like, you could prove things and like you see all the connections. All right. So like this is like you're like basically guaranteed an A if you get to that level of understanding. So like that's my style for like any math class is like yeah, if you I would even I'll even say here, if you're just like fluent in the techniques, you could still get an A and you can like just forget it when the class is over. But like what's special about this, when you reach that category, what's nice about this is like now like you will not forget it. Okay? Like you will not forget it. Okay? Or if you do forget it, it'll be easy to relearn. Okay? So you will not forget it, and then things are like easy to relearn. All right? Like that's why like anytime someone throws a question at me, like before, Jada, you threw me a motion problem, and I haven't looked at my lessons on motion problems in a while. But because I like spent the time to really like understand it and get it, like why does it work? I mean, proving why velocity is the derivative of position, like that's more just like a definition. But like, if you're like trying to reach these two, that's when you're gonna like really not lose it, okay? Because like just memorizing formulas is like it'll get you by, but you have to be like this is very stressful to just memorize the techniques and memorize the formulas. Like it works, but it's stressful. Like this is where you want to be if you want to like just like really go through the class. Like, and these are students, like I think of like some of the strongest students that I've ever had were always in this category. Like they were just seeing all the connections, they were proving everything. And like if it were Regents exams, they were getting like 95 and up. And if it was AP tests, like, yeah, they were just like, that's how they got fives. And I'm glad I took the time, like with students like that, at the end of the year, I'll have them write like a survival guide or ask them like, what did you do? But I like to pick their brain because, I don't see myself as like when I was in school, I wasn't like a top like 5% student. So when I'm spotting like the kids who are just like absolutely crushing it, I'm like, all right, please, like, I know I'm the teacher, but like, I want to know, like, what's your secret? Like, how are you like so good at this? And I still try to learn. I try to learn from people all the time, and students too. It's not like, oh, hey, I'm the teacher, I know everything. Like, no, I'm constantly picking up ideas from all of you. So, tips for managing time. I'm gonna real quick. I want to go to yeah. You know what? I'll answer the tips for managing time in that question. Then I'll do question 37. So I don't want to leave you bone. I don't want to leave you hanging there. So managing time is tough. That's something that I still struggle with. I would say for managing time, you have to make a schedule. Like if you really want to be like awesome at time management, like you really need to like almost treat it like you're like a CEO. And like when CEOs like start their day, they have like kind of like a planner, and they're like, all right, like 8 a.m., like blah, blah, blah. And then they're like 9 a.m., like blah, 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 blah. And then it'll be like 10 a.m., like to like, I don't know, 10:15 a.m. Like they'll say like, relax, wherever, whatever that means to you. And then like blah, 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 you continue. So the problem is if you're like, just going about your day like, you're just thinking like, okay, like blah blah blah, like yeah, I like Netflix and blah blah blah, like oh yeah, I should study math, like oh yeah, study math, let me do that now, okay, like blah blah blah, like do that, and like you're like, all right, I'm gonna go on my phone and blah, blah, like oh, I should study this. Like it's not organized. And like, yeah, if you put like crazy effort in, like you might see short-term results. But it's really about like having a schedule and following it consistently. Like the best pros in like any industry, whether it's sports or like academics, art, they have like a really intense system in place. And that's more valuable than the grade. And this is like from that book I was like mentioning before. I read this book, Atomic Habits, that if you put the right systems in place, like you're almost guaranteed the A. Like if you're following a schedule every day where you're putting in X amount of hours, and like the average student in your class is not, like, yeah, they could come in with like insane natural talent and like get by, but like for the most of us, like the average person, like it's all about the person who has like a better system in place. So I would say you got to schedule it, and stick to that schedule. Like this, for example, the live stream, I'm at the mercy of my two toddlers that they could wake up at any moment and just end this. But I'm telling myself, no matter how tired I am or whatever, I am going to live stream every Wednesday at 8:30, except holidays or something, but I'll mention that in advance. But I'm going to try to stick to it. And so far, it's like, all right, what week is this? Week 9 now? Or I forget where the title is. It's all the way at the top. But this is like the 9th week I'm doing it. So that's 9 in a row. And like that's when when I became the most productive. Like right now, once again, I'm struggling because like outside of work, I'm a dad of 2, so getting like the YouTube videos out there sometimes is a bit tricky. I keep a writing on my wall of all the videos that I want to make. And I have two lists. I have in front of the camera videos where I'm giving like general life advice. And then I have like the math topics I want to cover. And then like, sometimes I'll add a video to the queue that I'm like, ooh, this would be a good idea for a video. Like my students told me like, oh, make a video on calculator tips. So then like I still have my structure, but like I add it to the list and it's like in front of me so that I don't have to like, my brain has space now to not think about what I need to be doing. It's like just kind of scheduled out for me. All right. Because your mind is just like valuable space that you don't want to occupy with like trying to juggle everything and just do things randomly. It has to be, if you really want to be successful and like at that next level, like you want to be a professional, it's like you have a schedule that you stick to. Because professionals really just do things on a schedule, like even when it's like kind of boring for them, like, because there are times where like I don't feel like working, but like I do it and it's like, oh, I got to put a video together. Like I got to type out the template to like get it ready to shoot. So then like I'll put music on. So it's, if I'm doing something mindless that doesn't require critical thinking, then I'll put music on. You got to make it fun. There's ways around. Yeah. So that's managing time. Tomorrow's test, what topic would you say appears most often? I mean, I don't think that I have the actual test with me. I left that at work, but if I let me look up the course description on College Board. So let's see. So sure, I could be honest. I'll tell you what I remember. I mean, I can't make like promises, but yeah, an FRQ that will resemble what it is you need to look at. Sure, why not? Let's see. So all right, so unit 4, related rates shows up. I mean, I did the multiple choice. What kind of related rates was there? I mean, it's got a mix, but yeah, no, related rates is like, I would study this. So for my students, yeah, things to study related rates. There is a question on L'Hôpital. Okay. They spell it like this in the curriculum. So El Hospital. All right. So L'Hôpital, one question, that's not that bad. MVT, I'll star this one I'll star because it's like it shows up a bunch. This is like it shows up minimally. Extreme value theorem, this shows up, but I don't remember it being like crazy difficult. Okay, increasing. So this is like now here. Maybe I'll move this. So this is unit 4. So here, let me just unit 4, and now unit 5. So so now I'll write. Let me just clean this up a bit. So MVT is like not massive, but it's there. Extreme value theorem is, the ideas are big. Like I feel like this kind of connects well to like intervals where f is increasing, decreasing, like finding this one I'll star, like, because this is like part of a bigger idea. First derivative test, yeah, that's something that you should know. Concavity, and points of inflection, I would say, yeah, know that one. I did not put the second derivative test on there. Optimization, I'll say, is light. Like it's there, but yeah, this one is not worth a lot. Like it's one multiple choice question. So, and then, let's see. So an old topic I'll throw before this is implicit. Is like makes a short appearance, but like that's that kind of connects to this one. Like you're doing implicit when you're doing related rates anyway. And then like maybe there'll be like a basic derivative question as like an LOL to see who has mastered it. Okay, so these are like the starred ones are like the big topics. And let me see. Can you go over a similar question on related rates for the FRQ tomorrow? All right. One thing I will say. So the prize for people who came to the live stream to better themselves, for the FRQ, I would study the, I got to remember the handout that I gave you all. Study the handout from like related rates day. Okay. I don't know if you remember, maybe someone from class could say, the handout from that day, I forget how many questions I had on there, but if I may have given an AP style question with 3 parts. And if you remember that one, I believe if it wasn't the first day, it was the second day. Like when we did the trig stuff, that I gotta look back and see. But let me see here. I gotta check my my resources. So I gotta flick this off for a second. Because honestly, at Dory's comment, I would say the one I gave you in class today with the triangle, I would say that one like kind of covered a lot. But one tip I will give is today we looked at a situation where we had a right triangle and we had theta, and like if this was y, this was like 100. You may get a scenario like this where you have to know tangent theta equals y over x. And then if you take the derivative with respect to time, so this is something that's helpful. You'll have secant squared theta d theta dt equals quotient rule. So we have the low x times dy dt minus y dx dt over x squared. Okay, so low d high minus high d low over low low. So this, we may have to look at a situation where we actually have to do quotient rule. Just a thought, I would know this, all right? Being as subtle as I can here, but this is good to know. And also, another idea is that if, you know, let's say x is increasing, then that would mean like your dx over dt is positive. If y is, let's say, decreasing, so y is decreasing, then dy dt would be negative. Okay, so that's just something that I would know, because you may have a word problem where you have things that are like, let's say, moving, and like one of them's like moving away and one of them's moving like this. Okay, and you can see here, like, see y is decreasing because this object is moving this way, and x is increasing because the object is moving away, making x expand out. So I would say knowing this and this, plus what we did in the review today, will be really helpful. It'll give you an edge. Okay, so that's for that question, the related rates one. So I purposefully picked the triangle question. It's not, like I said, it's not exactly the same, but tomorrow's, you may need to know how to do this. And this may come into play. All right, cool. Whoever donates the most money, I will send them my packet of depression. Oh, that's funny. Packet of depression. Oh no. Is it a packet of fun? Oh, okay. So concavity when looking at a graph of f prime. So here, if let's say there's a graph of f prime and I have something like this. See, something like this. And you know what? Maybe I'll just name all of these. C1, C sub 2, C sub 3. So here, if we made a sign chart for f prime, actually, let me make it infinite. So f prime, notice there's two critical points where f prime is equal to 0. That's at C1 and at C3. And before C1, you see like here, the first derivative f prime, the graph is under the x-axis, so it's negative. And then between C1 and C2, it's positive and then negative, okay? Which would tell you the behavior of f is we're decreasing, increasing, decreasing. So from this, we could say f of C1 is a local minimum, f of C3 is a local maximum. But if we look here, what we have is, let's just see here. Oh, hello to Kenny. Oh, and Tori, thank you for the donation here and for the cool chomping level up. Or so Kenny, hello, my last year student. Kenny, we have a lot of students here from class that have an AP Calc test tomorrow. So I know that's all in the past for you. So I hope Calc 3 is going well. All right, so let's see here. For Max, you said, explain how to find concavity when looking at a graph of f prime. So what we have to understand is that concave up, you have to be able to say it like 5 different ways. So concave up would mean f double prime of x is greater than 0. However, if we have a graph of f prime, we have to think about how do you go from f prime to f double prime. You take a derivative with respect to x. So what we could say is, another way of saying this is that the derivative of f prime is greater than 0. Let me zoom out a little. But yet another way of saying this, so now we'll segue here. Yet another way, the derivative of f prime, derivative means slope. So we could say if the slope of f prime of x is greater than 0, then that means that our function is concave up. So you see here, like from negative infinity to C2, we have a positive slope. And another giveaway, the final way of saying it, the slope of f prime is positive. If your slope is positive, that means your function is increasing. So we could say when f prime is increasing. So this is at max, that 1, 2, 3, 4 different ways of showing that a function is concave up. If you could show the second derivative is positive, if you could show the derivative of f prime is positive, if you could show the slope of f prime is positive, if you could show f prime is increasing. The best way to do it for a graph, so once again, this is still at max. This down here, I'll like switch colors. This is the best for graphs, okay? Because it's visual, all right? Slope is positive, you need a graph to visualize that. When a function is increasing, the graph, if it's there, makes it easy to spot. So based on that, like how we have that drawn out, what I would say here is, so let's extend this page. So what I would say is that f is concave up on the interval from negative infinity to C sub 2 because f prime is increasing on that interval. All right, so that's the best way from a graph, in my opinion. So cool. Oh, Kenny, thank you. Wishing them luck. So let's see. Can you explain inverse derivatives? So yes. So this is at was it Sharon Bala or Bala? Sharon Bala. Sorry if I'm saying it wrong. All right, Max. Thank you. And look, I gotta for one thank you all for the. I know Jare and Richard shouted the what was it, the calculator tips video. They were like, oh, make that, like, you know, a few people chimed in on it, but just know that what's it called, like, I appreciate those ideas big time, because yeah, I think it was really like fun. So last thing I'll mention is the derivatives thing, because this time, like, I think last time I went way over by like a long time, so I will leave it at at this. All right, so moving on here, let's see. We've got the derivative of f inverse. All right, and all I'll ask is anybody new, if you haven't subscribed yet, I know I have that thing going in the corner, definitely subscribe, so that way you could, you know, come to all of, you know, any live stream that you could make if you need help. I'm here. And also anyone who doesn't have me for calculus or whatever subject you're here for help with, you can invite classmates, you know, like the more this grows, the better for all of us. So I'm really looking forward to this growing, and yeah, it should be cool, especially when we get closer to the AP test, or, you know, your end of year test for algebra, geometry, or trig, whatever you're here for. So, all right, let's see. Let me find questions from that problems book, because the problems book really has some good ones. So let's see, AP Calc problems book. Let me just write inverse. Hopefully this doesn't crash. Oh, it's freezing a bit. All right. For some reason, this giant book doesn't like control find. I guess the word is showing up too much. Oh, there we go. All right. Inverse. No, don't freeze. I mean, I can make up questions, but it's easier when, like, they're already made. All right. So page 51. Okay. So here, the derivative of f inverse. So find the derivative of the inverse of, and let's say we have, I don't know, let's say I pick f of x equals, and we've got something like 2x squared plus 10x plus 13. We'll say x is greater than negative 5 halves. So find the derivative of the inverse of f of x equals blah, 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 at, we'll say x equals 1. All right. So basically what we're finding is, we're finding, in this case, we're looking for what is f inverse prime at 1. So, like, and this is the formula for it. Now, if you don't know where that formula comes from, I always like to show a little proof. So I'll do this proof pretty quickly. Is if we have f of f inverse of x. So this is like what I was saying before. Like, proofs are really good for understanding. So the proof of this formula is this is the definition of an inverse. F of f inverse equals x. So if you take the derivative, you got to use the chain rule on the left side. That would be f prime, you keep the inside the same, times the derivative of f inverse. This is the notation for it. And then the derivative of the right side is 1. So if you want to solve for this piece, just this piece here, then you're going to have f inverse prime of x equals, and we have 1, and then you divide by this leftover piece. So the derivative of the inverse is really the chain rule in disguise. All right, so now coming over here, like I think what makes this question like a little annoying is you have to like really understand the relationship between a function and its inverse. So, so at Ricky, hello, nice to have you on, Ricky. Happy you could join us. Hope your, semesters are going, or your semester is going well, and it's like you all just like got started with college. All right, let's see. I guess it's a little better. All right, that's probably the best I could do. All right, so like any point here, x, y, if you look at the inverse, would switch to like y comma x. All right, so that's like an idea. So basically like what I'm getting at, if you really want to understand like inverses, let's say I have something random. Like if I have g of 1 equals 3, in inverse language, I would say g inverse of 3 is equal to 1. And that has to do with the fact that the x's and y's switch. All right. So here, they're telling us x is greater than -5/2. And the reason being, the only way a function has an inverse is if it passes the vertical and horizontal line test. So a parabola doesn't pass the horizontal line test. So what they're doing is they're restricting the domain at like, let's say the halfway point. So that if they cross this out, now it passes the horizontal line test. So that's just some background to know. But now, what we're ultimately trying to find here is 1 over f prime f inverse of 1. So if you want to know what is f inverse of 1, what you're really looking for is when is the function equal to 1. All right, we're looking for like, basically, I'm going to set this up. We're going to have 1 equals 2x squared plus 10x plus 13, and we go minus 1 minus 1. So we want to know when is the function equal to 1. So we have 0 equals 2x squared plus 10x plus 12. And if we scroll down a bit, we've got 0 equals x squared plus 5x plus 6. And now this is going to factor to x plus 2 times x plus 3. So x equals -2, x equals -3. But notice they said x has to be greater than, x is greater than, that's -2.5. So we have to go with this one. And now where that's going to take us, I'll transfer this over here. Get rid of this now. So we don't need this anymore. And I'll zoom out. So we get here, and that just told us that f of -2 is equal to 1. And if f of -2 equals 1, then f inverse of 1 is equal to -2. So then what we have is this piece. I will transfer. I'll transfer this over here. I'm going to find f prime, this step, is 4x plus 10. So what we have here is this is now equal to 1 over f prime of f inverse of 1 is equal to -2. And if I find what is f prime of -2, this is 4 times -2 plus 10. And -8 plus 10 is 2. So this is going to be equal to just 1/2. All right, so that's how you find the derivative of f inverse. All right, cool. That's, yeah, I would say for the instructional part, that's the best I could do. But yeah, once again, to anyone who swung by, so Ricky and Kenny, my old crew, very happy to have you both. And, hope college is going well. Any of my current students, thank you for stopping by, and, happy studying. Try to get some rest. I know, the night before a test can be stressful, but, you put in some honest work today. So, let yourself like relax a bit. And any students that I haven't taught in person, like in an actual classroom, my subscribers, I really appreciate you all for swinging by. So at Sharon Bala, I hope I kind of made that a little bit instructional. I could have just done an example, but I wanted you to like hopefully get the concept a bit. So if you need more help on that, I have a whole video on derivative of f inverse for AP calculus. Like I made one like 8 years ago that has a lot of views, but like the newer one I made, I think is better. It's got better audio and I covered more examples. So you could, check that out. Max, Story, Richard, Jada, thank you for swinging by. I hope it all goes well. But I'm just going to say good night, and hopefully I'll see some of you next week as well. So take care. Going to end the stream now.